Hello everyone, I'm going to deploy code to an embedded microcontroller and execute it. Traditional embedded development workflow take about 60 seconds. Watch this. This is the ESP32-P4 microcontroller and I want this C function to run on it. So in single Python file, we define the C code that include the C function that I want to run inside the microcontroller. Then I write the C code to file. Then initialize the P4 JIT and load the function. Then prepare the data. Then execute the function. Then return and verify the results. Less than a second, and faster than traditional workflow. And I can see the results directly in Python, visualize them, modify them, and iterate again. This is the P4 JIT, and it changes everything about embedded development. Let me show you how it works. Hi everyone, I am Bilal and I am working on my graduation project, which involves deploying a ULV10 nano object detection model to run on the ESP32-P4 microcontroller. Now, when I started this project, I immediately hit a fundamental problem. The traditional embedded development workflow looks like this. You write your code, you hit compile, wait 30 seconds, then you flash it to the device, another 30 seconds, you run your test, and if something's wrong, and let's be honest, something's always wrong at the first time, you go back, modify the code, and repeat the entire process. For optimizing neural network model, I estimate I need to do this at least 500 times. That's 8 hours of just waiting, just staring at the progress bar. That's when I had a realization. The development workflow itself is the bottleneck, not the hardware, not the algorithm, the tools. So before I could tackle my actual graduation project, I needed to solve this problem first. I need to build better tools. And that's how P4 JIT was born. P4 JIT stands for ESP32-P4, Just-in-Time Compilation System. But really, it's a development framework that lets you write high-performance C code, compile it on your PC, and dynamically load it into the ESP32-P4 in about 2 seconds. No firmware refreshing required. But here's what makes it special. It's not just about speed, it's about the entire workflow. You start in Python, your comfortable productive environment, you use NumPy to generate this data, maybe some signal processing, image manipulation, wherever you need. Then with one function call, P4 JIT compiles your C code, uploads it to the ESP32-P4 via USB, and executes it natively at 360 MHz, zero interpreter overhead, pure native RISC-V machine code. The ESP32-P4 processes your data. Maybe it's running a neural network layer, maybe it's a DSP filter, maybe it's a computer vision kernel, and then automatically sends the results back. And here's the magic. You're back in Python. The results are already in NumPy arrays. You can visualize them with matplotlib, analyze the performance, compare the algorithms, iterate again. The entire loop takes seconds. This is the workflow I wished existed when I started. So I built it. And I want to show you exactly how it works. Alright, let me walk you through a real example. I'm going to use audio processing tutorial. But remember, the accuracy of the algorithm isn't the point here. What matters is the workflow and the speed. Let's open the tutorial. First, I am in Python. Let me set up the environment. The environment is ready, and the source directory created. Now, I've already written my assembly kernel. Let me show you the source code. This is RISC-V assembly, floating point vector scaling. It loads a float, multiply it by gain vector, and store the results. Nothing fancy, just standard RISC-V instructions. Notice, it's using the floating point multiply instruction. This will run natively on the ESP32-P4 hardware floating point unit. File created, vector operations.s. Now, here's the C wrapper. Look at this carefully. It calls printf. That's the firmware's printf, not a stop. It reads the CPU counter using read cycle RISC-V assembly instruction. It calls the assembly kernel. Then it prints the performance metrics. All of this will execute as native machine code on the device. But watch what happens when I load it. Connecting to the device via USB. This line right here, JIT.log, is where the magic happens. Watch carefully. It's parsing the function signature from my C code. Then it's generating the wrapper code automatically. That's the bridge between Python and the device. It's compiling with the RISC-V GCC2 chain. It discovers the source files, the C code and the assembly code. It forms them automatically. Then it compiles them, then linking them together with link time optimization. That means cross-module aligning and dead code elimination. And the pass 1 completes. The pass 2, recompiling with real allocation addresses, compiling again, linking with firmware symbols, extracting the binary and uploading the function to the ESP32-P4 device, and done. The function is now loaded and ready to execute as native RISC-V machine code on the ESP32-P4. If this was traditional firmware rebuild, we'd still be waiting for the linker. That's the first key difference, iteration speed. Let me prepare some test data. I'm generating a 48,000 sample audio signal, a sine wave at 440 Hz. That's the musical note A, stored in NumPy array. This is what I want to process on the ESP32-P4. In the next cell, we define the location of the arrays in the ESP32-P4 memory. We define it in the internal SRAM of the ESP. Without running this cell, the default location is the external PSRAM, and there is many other options. Now let's call it. Let's call the C function that exists on the ESP32-P4 from Python. Watch how simple this is. Look at this line. Function, open parenthesis, input signal, output signal, np.in32, number of samples gain, close parenthesis. I am calling the function just like any Python function. I pass in my NumPy arrays, the length as integer 32, and the gain factor. Notice what I am not doing. I am not manually packing bytes. I am not dealing with pointers. I am not worrying about memory allocation. I am not computing buffer addresses. I am not writing wrapper code. P4 JIT handle all of that automatically. The smart args system allocate device memory for the arrays, transfer the data via USB, execute the native code, and read back the results. Watch. We get the execution cycles, the execution time, the efficiency, the throughput, and we get the output back. And it match the expected value. But here's what I really want you to notice. The output is already back in Python. It's a NumPy array. We can plot it using matplotlib and compare it to the expected array. And it's the same. This means that our C function runs as expected in the ESP32-P4 device with 0 error. Now while all this happening, the bus firmware on the ESP32-P4 was running in the background. The firmware implements the protocol. It receives commands over USB, allocates memory, writes your binary to device RAM, syncs the cache, and executes your code. It also provides those functions like printf that your JIT code can call. The firmware is the server, P4 JIT is the client, and they communicate over binary protocol at 12 MHz per second. This is the firmware location in the repository. You must flash it to the ESP32-P4 using IDF first. And if you were watching the device monitor, you would have seen this output from those printf calls. Those calls. Passing to the firmware. So this terminal is connecting to the ESP32-P4 via UART cable. This is the UART cable. This is the USB cable. So we can see the output in the firmware terminal. Now let me show you something really important about what actually got uploaded to the device. I'm going to generate the disassembly. That's the actual RISC-V machine code. Disassembly saved. Now look at this carefully. This is the actual machine code that runs on the ESP32-P4. Let's find the interesting part. This is our wrapper function carry mode. See these instructions? They loading the arguments buffer, address, reading argument 0, reading argument 1, reading floating argument. That's the wrapper reading our arguments from memory, exactly like tab.c code we saw. Now look. Look here. This is where it calls printf. See this instruction? That's jump and link register, a function call. The address is calling is the firmware's printf. And here's what's crucial. Do you see any printf source code in this assembly? No. Do you see any string formatting logic? No. Do you see any serial port access? No. There's just the call, because we link it against the bus firmware L file. The link arrays of printf to the address where printf live in the firmware. Our JIT code, just call it, zero overhead, direct function call, no stop, no wrapper, no reimplementation. This is why our entire binary is 4 kilobytes. We are not carrying around a printf implementation or malloc or any standard library. We are using the firmware functions. The firmware has all of that. Printf is probably 15 to 20 kilobytes of code. For formatting, buffering, serial output, we don't include any of it. We just call it. And here our assembly kernel. Look at the look, it's very clean. Plot float from input array, multiply by scale factor using hardware floating point, store to output array, branch back if not done. That's hand optimized assembly, running at full CPU speed with zero interpreter overhead. This is the real embedded system code. The firmware L file I am linking against is the firmware/build directory. That's the bus firmware that was flashed once to the device. It contains the printf malloc free, all of the ESP-IDF functions, free RTOS, everything. It's several megabytes. But my JIT code, 4 kilobytes. Because it's just calling functions that already exist in the running framework. That's the power of the symbol bridge. And all of this happened automatically. Now, the introduction tutorial showed you the basic workflow, 2-second iteration cycles, seamless Python integration, native RISC-V execution. But there's where the P4 JIT becomes truly essential. This notebook implements digit classification using quantized neural network. But this isn't just any embedded ML project. This code uses ESP32-P4 PIE SIMD instructions. Let me explain what that matters. The ESP32-P4 has custom SIMD extensions. They are called PIE instructions. Things like .product, hardware loop. These instructions do not exist in the standard RISC-V specification. Traditional embedded ML workflow, you train your model, quantize it, test in the simulator like QEMU or Spike, then flash to the hardware. But here's the problem. QEMU doesn't know what parallel.product means. Spike doesn't know about the hardware loop instruction. These are the hardware specific extensions. The simulator will throw illegal instruction exception. You cannot test this code without real hardware. With P4 JIT, then quantize, write your code, inline assembly with the PIE instructions, compile with the ESP32-P4 JIT to chain, deploy in 2 seconds. Test on real silicon, the hardware knows these instructions. They execute natively, and you get the result immediately. With the P4 JIT, here's the final fully connected layer using PIE SIMD. Look at this assembly block. There is .product instruction with parallel execution. It processes 60 parallel 8-bit multiply with accumulation. This process 16 ways per iteration. Without the P4 JIT, you'd need to rebuild the entire firmware every time you tweak this loop. With the P4 JIT, 2 seconds, test iterate. The result, 10 of 10 test digits classified correctly. Perfect accuracy on the test set. Consistent timing across all digits. The full notebook works through the complete pipeline. int8 quantization with power of 2 scaling, quantization over training, correct bias scaling, MOT, weight extraction, C implementation with the PIE assembly, deployment and validation. It's all there. If you want to understand how to deploy quantized neural networks on embedded device, real embedded device, not simulator, this notebook shows you the entire workflow. But the key takeaway is this: you cannot develop code with custom ISA extension using traditional tools. You need either very slow firmware rebuild cycles, or you need P4 JIT. That's the game changer. The notebook is in the repository. Check it out, run it yourself, modify the assembly, try different quantization strategies. The iteration cycle is fast enough that you can actually experiment. That's the power of the P4 JIT for embedded machine learning. Now, I've only scratched the surface here. There are many more examples I didn't cover in this video. P4 JIT supports C++ code. You can write object-oriented embedded code and deploy it in seconds. There are examples showing bidirectional array synchronization, where arrays modified on device automatically sync back to Python. There are heap monitoring, firmware symbol linking with malloc and free, multi-file compilation with link time optimization across C, C++ and assembly files. All of these examples are in the repository. Check the README file. It has a quick start guide and links to every example. The test folder has complete working demos, advanced type handling, struct manipulation, memory allocation strategies. Everything is documented and ready to run. And if you want the complete technical specification, every detail about protocol, the memory system, the type system, the build pipeline, that's all in the TRM.md, the technical reference manual. It's a comprehensive document that explains exactly how everything works under the hood. Look, embedded development has been stuck with slow iteration cycles for decades. 30 to 60 seconds to test single line change. Before she changed that. 2-second cycle. Native performance, real hardware, Python integration. This is how embedded development should work. If you want this useful, please give the repository a star on GitHub. It helps others discover the project. And if you build something with the P4 JIT, I love to hear about it. Open an issue, start a discussion, share your code and your work. The link to the repository is in the description below. The code is on MIT license. Use it, modify it, build amazing things with it. Thank you for watching and happy coding.